Swayam Prabha. Digital India. Educated India.
Dear students, today's is the fourth lecture in the series on consolidation and settlement. You will recall that in the previous three lectures, we had devoted considerable amount of time and discussion to the physical aspects of the phenomenon of consolidation. To put it in a nutshell, I had described the phenomenon of consolidation and the resulting settlement as a phenomenon which is predominantly observed in clays, and that too saturated clays. It is primarily a process in which when a load is applied to a saturated clay layer in the form of say a building or some construction activity, then since clays are very poorly pervious, the water requires considerable amount of time to move out of the pores of the soil. This is known as hydrodynamic lag. They take a long time in view of the low permeability of the clay layer, that the resulting readjustment of the solid particles and their reorientation and the resulting compression always lag slightly behind the process of hydrodynamics. So, this entire phenomenon is known as hydrodynamic lag, and therefore, this compression phenomenon under a load is basically a product of or a result of the gradual movement of water out of the pores of the soil due to a gradual application of a load. The word gradual is very important both from point of view of application of the load and from point of view of expulsion of water, because we will be probably seeing in some other lecture in another topic the impact of sudden loading. When there is a sudden load, the phenomenon is not the same as what we are now reviewing under the topic of consolidation. Well, so consolidation and resulting settlement is primarily observed in clays, saturated clays in particular. It is particularly important only mainly for saturated clays, and it is a result of gradual expulsion of water when a load is applied. Now, this aspect needs to be put in mathematical terms so that we can evolve a theory. This also we had briefly seen, an introduction to this we had discussed in the past few lectures. We referred to it by the name one dimensional consolidation. I had described a theory which we shall be discussing in more detail today and later as the one dimensional consolidation theory. This phenomenon of one dimensional consolidation considerably simplifies the process of consolidation and makes it much easier for us to understand and describe it mathematically, and also to make predictions about settlements with a reasonable degree of accuracy from practical point of view. Imagine there is a soil, imagine we construct a foundation and then a superstructure on it. The process of construction definitely takes some amount of time. It is not an instantaneous process. This gradual process transfers the load to the soil below very gradually, and correspondingly in a very slow manner water is expelled out of the soil, and therefore, the resulting compression also follows suit very slowly and gradually, and this in fact is the cause of concern for us. Although gradual, it is actually a matter of concern. The concern is that this compression could take place gradually over a long period of time during the lifetime of the structure, which means that at some point of time during its life, this compression may exceed certain acceptable or permissible values, which means that up to some point of time the structure may be apparently behaving very satisfactorily, performing very satisfactorily, but at some point of time it will start showing distress, because the settlement would have probably exceeded some acceptable or permissible value for that combination of structure and the soil, and this is the cause of concern, and this requires that we be able to compute the total settlement that the building is likely to undergo, and not only that, we also need to know at what rate it is going to take place. All this we had discussed, and we also saw in the previous lectures how the total settlement can be computed. It so happens that irrespective of how much time it takes, the total settlement that a building will undergo depends on the void ratio change, on the pressure, total pressure that is applied, and the pressure void ratio relationship. It actually does not really depend upon the magnitude of the rate at which the water is expelled. It actually simply depends upon the total load applied and the total resulting void ratio change or volumetric change in the soil. Therefore, the total settlement we could compute very easily. We saw in fact two examples of computation of total settlement in the previous lectures in very great detail. These examples had shown very clearly that computation of total settlement really does not involve any complications, and once we know the initial and the final void ratios of the soil corresponding to the initial state of stress and the final state of loading and corresponding stress, we can compute the total settlement. We saw two examples of this, and we concluded by saying that the relationship between E and P can be taken as logarithmic, and a very convenient linear relationship can therefore be formulated between E and P, and that can be used in the computation of the total settlement. Now, today we shall proceed further to see the next aspect, that is the time rate of consolidation. Fortunately or unfortunately, though it is possible to compute the time rate of settlement very well, it is somewhat involved and it requires a detailed mathematical treatment of the subject. We shall proceed step by step. To begin with, we will see some essentials or some fundamentals or prelude to the computation or evolution of a computation procedure for time rate of settlement. So, let us see the next slide to sum up what we had seen in the past. A summary of what we had seen in the past is what is shown in this slide. As you can see, we discussed in detail first of all the odometer test, because it is the odometer test which gives us the pressure versus void ratio or void ratio versus pressure relationship. And it is this void ratio versus pressure relationship which we get from the odometer test that we idealize into a straight line in the semi-log plot. Once we idealize this into a semi-log plot into a straight line, we find that a very convenient simple parameter called the compression index can be thought of to relate E with log P, and this serves as the basis for computation of the total settlement. Then we saw compression behavior of clays in general in order to lead to the importance of the time rate of settlement. We saw, for example, that compared to sands, in clays under the application of load, there is a long duration over which the compression takes place. In case of sands, much of the compression takes place almost instantaneously or during the erection of the structure itself, and therefore, there are no time dependent compressions which are manifested during the lifetime of the structure, but not so in clays. In clays, we always expect, we always find time dependent long duration consolidation and settlement. Then and this was illustrated very nicely by typical odometer test results, particularly the E log P relationship. Then we started discussing the theory of one dimensional consolidation. First of all, we said that one dimensional consolidation is an assumption, said that it is valid under certain specific circumstances. The major circumstances under which this is valid are: 1, a very large loaded area, a deep seated clay layer. These are sufficient to justify that the loading is uniform over a small range of the clay layer at the center of the clay layer, and we are justified in assuming that the entire flow of water, expulsion of water is one dimension, and the corresponding compression is also in one dimension. Let us see what to discuss further in today's lecture. In today's lecture, we will continue with this discussion on the one dimensional consolidation and go towards evolution of a mathematical description or a computation procedure. First, let us take an overview of this before we actually take up discussion of the mathematics involved in the problem. In the overview, we shall be discussing certain parameters that we will eventually be using to describe the void ratio time pressure relationship. We will also be seeing an analogy which is similar to the consolidation phenomenon, but is much easier to comprehend and which helps us to understand the consolidation phenomenon much more easily than any other way. So, let us take a look at what are the parameters that are available to us for describing compressibility. We have already defined, in fact, one particular parameter, and that is the compression index, and we saw that the compression index can be determined from a typical E log P curve, provided the curve is drawn as a semi log plot, and from an E log P curve we can determine Cc, the compression index, as the slope of the compression virgin compression curve, and the expression for compression index is negative. It being as negative slope, it will be minus of change in void ratio by log of the ratio of the final to the initial effective stress. Now, we come to a very important parameter, which is what is essentially useful in time rate of settlement calculation. This parameter also defines compression in some ways, but it is different from the compression index in the sense here we do not make any assumption regarding straight line relationship in a logarithmic plot. We in fact take a relationship directly from the E P or E sigma dash curve. The E sigma dash P curve or P curve is shown here. It need not necessarily be linear, but any small segment of this if we take and consider it to be fairly linear, then once again we can effectively describe the rate of the change in void ratio as a function of the change in stress, and that parameter is what is known as coefficient of compressibility, and that is equal to the change in void ratio divided by the change in stress, both being taken as positive. So, here is a summary of the parameters that are normally used for describing compressibility. In addition to the two parameters which we have just now discussed, I have also added another parameter here. The first one is, as I said, minus delta E log sigma 2 dash by sigma 1 dash. Now, it is not always convenient to use a negative quantity, and therefore, the change in void ratio is expressed as E1 minus E2, and for convenience the negative parameter is converted into a positive parameter and used. Now, the coefficient of compressibility is delta E by delta sigma dash, and this helps us in fact to compute the change in void ratio as a function of change in pressure, and this can further be modified into yet another parameter, which is known as coefficient of volume decrease or coefficient of volume change or coefficient of volume compressibility. There is a subtle difference between the coefficient of compressibility and the coefficient of volume compressibility. See here, this parameter is known as MV. This parameter is defined as change in volume per unit volume as a ratio with respect to the change in stress. So, earlier it was merely the change in void ratio, which in effect is nothing but the change in volume, whereas now it is change in volume per unit volume with respect to the change in stress. So, this will be in terms of void ratio delta E divided by 1 plus E 0 divided by delta sigma dash. This, if we try to relate it to the coefficient of compressibility, which is also a very important and convenient parameter, then we get that this parameter MV is nothing but AV divided upon the original volume of the sample or soil, which is 1 plus E 0. So, we have two parameters, delta E by delta sigma dash and AV by 1 plus E 0, and these two are based on a E log P curve, which is the natural relationship and not an idealized logarithmic linear relationship. And these two are what are found to be useful for determining the rate of change of settlement or rate of change of compression in the soil under the application of load. Now, how we can possibly relate this with the rate of change? A little bit of thought will tell us that this parameter after all represents the change in stress. It represents in some way the change in the compression as a function of change in stress. Now, if we go back to our earlier discussion, we will find that we had expressed this phenomenon of consolidation as a gradual process of expulsion of water and corresponding transfer of stress to the solid grains. The word stress there very clearly shows that there is something that relates the stress with the gradual process of expulsion of water and the transfer of stress from water to the solid grains. So, we can easily see that there is some kind of a relationship there in the very definition of the process between the transfer of stress and the change in stress and the change in void ratio as a result of flow of water. So, the rate of flow of water can be sequentially related to the volume change and then the stress change, and this is the kind of approach which was thought of by Terzaghi in developing the so called one dimensional consolidation theory, wherein he gives as an excellent mathematical method for computing the rate of settlement and predict the rate of settlement when we are given a certain stress change due to a certain activity, construction activity in a given soil, and when we know what is the permeability of the soil and what would be the rate at which water will be flowing out of that soil. So, given a soil, if we know its